We've been discussing about fluid flow for a while now, and we haven't yet discussed the thing that usually makes fluid flow other than gravity, no? And among the most common equipment is a centrifugal pump, as you will see in the video um, with the link on the next slide. So, pinakasikat po ang centrifugal pump. It's used mostly for low viscosity liquids, especially those which require high flow rates and moderate pressure. Another advantage is that you can also use this for liquids containing small particulates such as water transporting green peas. However, the disadvantage would be that this could not be used for very viscous fluids, yung may consistency na syrup pataas. Personally, I've seen this in action in the ice cream industry. This is what we use to transport the liquid mix prior to aeration across the plant over hundreds of meters of piping from one section to another, from a tank to the freezer, or let's say from the mixing area to the aging area, and so on. So please watch this video to the end. It's a very good introduction to centrifugal pumps and their basic concepts and parts. So to summarize from the video, the basic parts of the centrifugal pump are as follows. There is this motor which provides the energy transferred to water to increase the energy of water and allow it to flow. Okay, and this is what we call an impeller, the rotating thing. The eye is where the fluid enters. So take note, hindi siya yung diretso lang, no? Yung daloy, may 90 degrees in three-dimensional space. Pagpasok mo, 90 degrees yung labas nung fluid because of how it needs to be swirled around by the impeller to increase its energy. Ang maganda rito ay pwede siya gamitin sa clean in place systems, hindi naman siya ganun kaselan except for yun nga kailangan hindi mag-implode yung bubbles which may cause damage, and the flow rate is typically controlled at the discharge by the opening of the valve rather than the RPM of the motor per se, no? So, mas simple na dito sa pagkaharang sa kanya, dun mo na lang i-control yung lakas ng daloy. And the main principle here, again, is increasing the liquid pressure as it goes from the suction to the discharge. Again, take note of the pump's need for priming. Hindi siya nga pwedeng parang straw na hihigop ka lang. Kailangan submerged na yung buong pump mo sa liquid before you operate it para hindi siya masira. So just some terms. When we hear the term head, it refers to technically the height of a fluid which can be supported by the pressure acting on it ng pump, given by rho g h. So ayan yung head, yung H. So technically kapag nakita ka ng pump, usually sasabihin nila sa'yo kung ano yung pump head niya. Okay? Parang isa yun sa mga technical specifications niya. And that simply means that this is the theoretical possible highest height na kaya mong ibato yung tubig pataas, no? Kasi usually naman yun yung purpose ng pump yung vertical distance na kaya mong iangat yung tubig para pumunta sa tangke or kung saan mang production area mo kailangan. Okay, if you have a pump at home, maybe for your water, you could probably look at the technical specifications on that pump, and usually meron siyang head na naka-indicate. So, of course, there are two types of head, the suction head and the discharge head, which is a summary of the pump power requirements in terms of head on the suction and discharge side, respectively. So, magkaiba po yun. Okay, yung kayang sipsipin ng pump pataas dun sa suction side at yung kayang ibuga. Okay? Usually, mas malaki ang discharge head sa suction head. Kasi sa suction head, kapag mas malaki sa suction head yung height ng pagsisipsipan mo from the tank level, like galing siya sa baba ng tank, pwede ka mag-cause ng cavitation. So in looking at the basic head requirements, you want to look at the nature of the system. Okay. So this here is the suction side and this here is the discharge side. The total head in this case refers to practically yung total amount of work in terms of pushing or siphoning a liquid up na kailangan nung pump. Okay. So in this case, you have to pump the liquid. You have to overcome the 10 meters high na static pressure ng fluid on this side. So that's this one. However, may tulong ka galing sa suction side kasi yung static head naman nitong 5 meters na to, essentially tinutulak niya, binabawasan niya yung effort na kailangan gawin ng pump. Okay? So, in short, this 10 meters less this 5 meters, yung total work na lang na kailangan gawin ng pump is 5 meters total head. Okay? Of course, this does not take into account yung mga friction dun sa system mo, etc. Basic assumption to. Okay, so that's the first case. So, less yung effort ng pump kasi mas mataas yung liquid level sa suction side kesa dun sa level ng pump. Right, so in this case naman, it's the same as case A. However, if we look at the area here, so yung reading ng pressure dito ay mas mababa na kesa dun sa case A, which means that there are frictional losses, okay, that have been accounted for. So in real life situations, as you mentioned, di ba, may friction yan sa elbow, may friction sa length ng pipe, may friction sa either pag-constrict or paglaki ng butas. And minsan, yung equipment mismo may friction factors and contribution. So in this case, the head is measured by measuring the pressure at the inlet and outlet side of the pump. Okay. So what about in a situation wherein the liquid level of the tank is lower than the pump itself? So yung suction side, mag-e-exert ngayon ng effort si pump mo para mahigop yung fluid na parang straw. So meron kang suction head dito. Okay. So, dalawa yung effort mo kasi sisipsipin mo na siya pataas, tutulakin mo pa siya pataas. So, yung total head, which is a suction plus a discharge head, would now be the sum of the total effort na kailangan gawin nung pump para ma-accomplish yung kanyang goal to transport si volume of liquid from this point all the way to this point. So, yung delta H mo yung change in height mo na 17 meters. Yun yung effort na kailangan gawin ni pump. Okay? So finally, we have a case wherein one of the sides are pressurized. Okay? So in this case, for example, merong pressure na 3 bars yung sa suction side. No? So, enclosed na tangke siya na may air pressure dun sa taas. So, that pressure actually helps push the fluid on top of the static pressure from the height of the fluid to further lessen your your pump's head requirements, no? So, in this case, yung total head niya would be equal to yung kailangan may overcome na height less yung height dun sa suction side less yung equivalent height ng pagkakaroon mo ng pressurized na tank. So this case, you would need much less effort of just 2 meters of head for your pump, to be able to do its work. So when we're looking at the pump performance characteristics, itipin mo ito yung technical specifications na required for the pump. Kasi ang pump, pwede mo siyang gamitin sa a variety of different systems, okay? And syempre meron yan yung maximum power na kaya niyang i-output, yung maximum suction height na kaya niya, maximum discharge height, etc. And then maybe other characteristics such as fitness for use na varying viscosities of fluid and so on. And ano yung pinaka efficient niya na point, no? Kasi pag magde-design ka ng system, bawa meron kang bahay man lang nagagawin, tapos gusto mo maglagay ng pump kasi may water tank ka dahil sa area niya nawawala ng tubig, no? That pump has to be the appropriate size for the intended use. Gaano ka laki ba yung pipe system, gaano kataas mo ibabato, what is the expected flow rate na tawag dito, flow rate ng tubig dun sa pipes mo, okay? Based dun sa usage level ng bahay, no? Kasi pag oversized, lugi ka naman, malakas siyang kumonsumo, tapos hindi mo naman na-utilize yung best efficiency niya. Similarly, pag masyadong maliit, hirap na hirap siyang gawin yung trabaho niya kahit kaya naman technically nung range ng pump na gawin yun, or pwede siya mag-overheat. So the power output of the pump is simply equal to the mass flow rate multiplied by the acceleration due to gravity multiplied by the pump head. Or similarly, the mass flow rate is equal to volumetric flow rate multiplied by density, since usually mas madaling mag-measure ng volumetric flow rate, no? Unless sasahurin mo dun sa dulo tapos titimbangin mo yung na-collect mo over a specific period of time. Okay? So that means, since we're basing it on mass flow rate, if you have two fluids of the same volumetric flow rate but different densities, then there would be a difference in the let's say power requirements. Then we also have this term called the brake power, which is simply the product of the torque multiplied by the angular velocity of the pump shaft. So efficiency then is just a ratio between the actual power that you can transmit to your fluid over what is theoretically the power consumed by the pump. So in essence, ganyan naman lahat ng efficiency calculations natin. How much of the power that you are consuming is actually doing useful work, okay? Alright, so in this case, you are given a pumping water at 30 degrees Celsius with 15,000 liters per hour flow rate, and then we are asked to calculate the pump head and power requirements given that the measured suction and discharge pressures are as follows. Okay, so of course we would use the pump equation, power requirement equation, wherein there is a volumetric flow rate. So from the temperature of water, we determine the density value. Of course, we know what G is, and from the suction and discharge pressure, we determine the pump head, of course, converted accordingly. So to solve this problem for the pump head, we take the discharge pressure minus suction pressure, convert that into kilopascal so that we could multiply it to, divide it rather by the density and acceleration due to gravity to get our pump head equal to 30.71 meters. For the power requirements, instead of using the pump head and multiplying it back again, let's just use the pressure, since pressure is equal to rho GH. So para pressure na lang multiplied by the volumetric flow rate. Okay, so that's 3 100,000 pascals multiplied by 50,000 liters is 15 cubic meters, and 1 hour is 3,600 seconds. You get a value of 1,250 kilogram meters squared per second cube, which is actually equal to a watt. So therefore, we have 1.25 kilowatts. So to put this into perspective, this pump running at this power requirement for 1 hour would consume about 13 pesos worth of electricity. And in terms of electric fans at 40 watts, then that's like having 31, 40 watt, 32, 40 watt electric fans running simultaneously. Okay. So in the next slide, we'll see an example of the pump characteristic diagram. Maraming information doon, as you can see here, regarding flow rate, efficiency, brake power, and so on. Since pumps are usually tested using water, which is widely available, if gagamitin siya sa ibang fluids, kailangan i-adjust definitely because a change in the viscosity or density of the fluid will affect yung performance ng pump. Okay, so for the head, there is the volumetric flow rate, which could be either rising, drooping, steep, or flat. And the curve on the pump characteristic diagram usually also depends on the design and construction, especially yung type ng impeller. And then when the pump is flowing but the throttle valve is off, thus the volumetric flow rate is 0. If we apply energy balance, dahil may kinokonsume kang energy pero walang flow na nagaganap, then that energy becomes translated into heat. So here is the example of the pump characteristic diagram. On the x-axis, you have volumetric flow rate in cubic meters per second. So 0.005 is 5 liters per second. Okay. And this 1.015 is 15 liters per second. Medyo malaki yun kung isipin nyo, no, kumpara sa gripo natin sa bahay. Relatively mabilis na daloy ito ng tubig. Okay, and on the y-axis, you have either the head in meters, depending on which curve you're looking at, or the efficiency in percent. No? As we've noted before, the efficiency is the ratio of the power consumed versus the power that's actually meant to do useful work. Okay, and we have the terms here which we'll discuss one by one. So as you can see here, yung head ng pump is dependent on the flow rate, and definitely we could see here na bumababa yung head, the faster the flow rate is, because kapag mas mataas yung flow rate mo, you would need more energy to push the water up a certain height, and therefore it makes sense na at lower volumetric flow rates, mas mataas yung height na napupush niya given the energy na kayang i-deliver ng pump. Okay, of course, there are design limitations. As you can see, hindi naman siya tipong at half the volumetric flow rate, doble yung head, no? Parang hindi ganon yung curve niya. Then we also have the efficiency curve, which tells us basically saan yung optimal range na gamitin yung pump. So if you're designing a pump, you want to match it to the flow rate at the best efficiency point, which is yung peak ng efficiency curve. So basically this pump is designed for around 0.009 something cubic meters per second, or slightly less than 10 liters per minute yung operational niya na best operational point. So ito siguro, no? The system curve is a function of the system. Ang mahalaga lang dito is dapat mas mataas yung curve ng pump dun sa system curve. Kasi the moment halimbawa dito nag-intersect sila, and then at this point, mas mataas na yung system kesa dun sa pump head curve, then that simply means hindi na gagana yung pump mo, hindi na niya ma-accomplish yung goal of moving the fluid throughout your system beyond this volumetric flow rate kung saan sila nag-intersect. NPSHR, as will be discussed in a while, is a net positive suction head required. It is a function of your system as well. And ang mahalaga lang din is mas mataas din yung head curve mo sa yung net positive suction head available mo sa what is required. So again, let me stress that a pump is designed to operate at near peak efficiency. So you can push it up faster or way slower than sa peak efficiency, but then again, magsasayang kayo ng energy, which is usually kuryente ang ginagamit. So you want the pump to be near, or you always operate near the best efficiency point and select a suitably sized pump for that expected flow rate. Okay, and then the use of a different impeller diameter or usually shifts the head curve upward kung mas malaki yung impeller mo. So we'll see examples later of curve shifting. As you've probably seen in the earlier video, so may nabanggit yung phenomena ng cavitation. And to prevent this cavitation, which is yung pag-boil or pag-evaporate ng water because of the lower vapor pressure inside the system dahil nga may suction ka, may vacuum na nagaganap. And we know that in vacuum, water evaporates at a lower temperature. There is what we call the net positive suction head. So meron tayong net positive suction head available and net positive suction head required. So simply put, NPSHR is the minimum value that you need to have para hindi mag-occur yung cavitation. So when you're looking at a pump used to be used in a certain system, you need to calculate the NPSHR and make sure under those conditions na mag-exceed doon yung NPSHA or yung net positive suction head available. So this is simply suction head less the vapor pressure over your rho G. Okay, and then since the suction head can be determined using this equation, so you can calculate the NPSHR. So the net positive suction head available or NPSHA is a function of the pump pipe system. So nagbabago yun depende kung nilipat mo yung pump elsewhere, etc. And basically you just need the NPSHA to be greater than the NPSHR for the system to work. And the net positive suction head available is equal to the suction head minus the vapor pressure head, okay, as indicated in this equation. So consider this illustration where you have the reference plane, which is 0.2, and then the suction side, which is 0.1, which in this case is below the pump. So you have your height Z1, which is the difference from the reference plane to the surface of your suction side. Okay. Then you have the pressure at 0.2 at the pump, P2. Mu is the velocity of the fluid traveling. So this is dependent also on the pipe diameter in that case. You have the density values here and then acceleration due to gravity. And PATM is just the atmospheric pressure, which is a function of the temperature and usually the elevation of your area, kung sakali man nasa bundok ka or something. So now we look at paano ba tayo nagsiselect ng isang pump for a certain system. Of course, we have to look at where the pump will be located kasi nga yung suction and discharge side ay mahalaga na hatiin natin. Okay, and then of course we're gonna look at the flow rates, etc. and other factors. So take for example, we have the system head, which is of course dependent on system elevation, fluid elevation, and other things. This is given by the difference in the height between the discharge and suction side. Kasi yun yung kailangan mong i-overcome na height difference. And you have to take into account the frictional losses denoted by H sub 1-2. Okay. And this frictional losses is equal to a certain constant that we could measure experimentally, C system, which is multiplied by the square of the volumetric flow rate. So friction increases with volumetric flow rate or fluid velocity, in a sense, the square of it, no? So parang ito yung proportionator mo. Therefore, the system head is equal to the difference in the elevation plus the total of the friction losses, which is also a function of the volumetric flow rate na ginagamit mo. Remember, of course, that we can vary volumetric flow rate through the throttling valve. So to illustrate yung nasa previous slide na equation, this is the system head curve. There's an overhead term here, the total static head, yung difference ng heights nila. And then these are the frictional losses, which vary exponentially with increasing volumetric flow rate. So the system's head curve, which the pump must overcome, is something that increases with volumetric flow rate, not just because of the static head you need to overcome, but more so because nag-i-increase yung friction. So actually, the higher head needed at higher flow rates is to counteract the increase in frictional losses, which is exponential. Okay, here we can see naman na yung system head curve natin ay nag-shift, minimum and maximum head curve. Imagine nyo na lang yung tangke, di ba? Kapag nade-drain yung tank sa suction side, at the same time, tumataas yung level ng tank dun sa discharge side, nagbabago yung difference ng height nila, nag-i-increase yung gap. No? Kasi suction side bumababa, discharge side tumataas. So therefore, hindi ito constant throughout the pumping process. Okay, there are cases wherein the system head curve would increase as the pumping process continues, no? So ito yung tinatawag nating shift in the curve, as you can see. And we have to take that into account when selecting our pumps. So yung pump capacity curve mo, hindi yan nagbabago. Pero anong ibig sabihin nito? Kapag nag-shift yung curve mo upwards, so this is the first curve, the minimum, then it shifts upward as you go on kasi nag-change yung difference in height. Yung maximum flow rate na kaya mong gamitin para ma-overcome yung system head ay mas mababa na. So at the start, you can use this flow rate, for example. Then habang papuno na yung tangke, pababa ng pababa yung max flow rate mo to this one. So on the other hand, when you regulate the throttling valve, which is basically yung opening na dinadaluyan ng tubo na nag-restrict ng flow, parang sa gripo lang, di ba yung valve ng gripo, nag-change din yung system head curve. So this one is, for example, fully open. Then if you partially close it, and then mas malapit sa closed than open, for example. So in short, mas pinakamaganda yung setting niya pag open yung throttling valve, fully open. And then, since siyempre, nag-restrict ka ng flow, yung frictional losses mo lumalaki, di ba? Kasi iniipit mo siya. So in general, anything that would contribute a friction loss in the system would shift the curve towards the left. And of course, we know that kapag towards the left yung shift niya, mas mababa yung magagamit nating maximum flow rate, no? So that's what's important, no? Kasi ang titignan lang natin is in terms of yung intersection ng system head curve at pump head curve, you want it as far right as possible, di ba? And kung mag-shift siya to the left, that means marirestrict yung use natin. So the throttling valve is independent from the pump rotation speed, no? You can adjust the throttling valve for a certain pump rotation speed to adjust the flow. However, it's also possible to control the pump speed, rotation speed. And as you can see here, kapag ina-adjust mo yung pump rotation speed, ay lumalaki din yung pump head. Okay? So, parang rainbow, no? So, as you can see here, yung H1, mas malaki yung volumetric flow capacity niya than the H2 and H3. Okay, so let's look at the formulas that govern pump performance. N is the impeller speed. So dimensionless naman yan kasi nagka-cancel out sila. You can have it in whatever RPM or ano mang unit na gusto mo. The volumetric flow rate is proportional to the increase in propeller speed. Therefore, if I run at 1000 RPM and then run at 2000 RPM, edi doble na agad yung kaya kong output. Tapos, yung kanyang head ng pump, okay, this is not system head, this is pump head, ay exponential yung increase. So, if I double the speed from 1000 to 2000 RPM, I could get 4 times the pump head. Di, ang ganda pala sana niya kung ganon. Kasi, sige, doble ko yung RPM, I get 4 times the head. But the problem is, I do get 4 times the head, but at what cost? At 8 times the power requirement. Okay? So, isipin niyo parang sa kotse lang yan, di ba? Pag tumatakbo kayo, kung gusto mong humarurot, sige, paluin mo ng 6,000 RPM para mag-accelerate ka. Mabilis ang acceleration mo, you get high speed agad, pero lumulunok naman ng gasolina yung sasakyan mo. So parang ganun lang, and that's why even though most cars can run at a very high speed, there's usually a cruising speed that you want them to run. No, other than legal limits of course, pero more on for efficiency. Okay, so ganun din yung pumps kasi mga motor din naman yan eh. Umiikot na bagay din yung mga yan. So I hope you're still with me. Let's now go to the last segment, which is how do we measure flow, no? Kasi nakita naman natin ang dami nating ginagawa. Pero lahat ng ito nakadepend kung masukat mo yung volumetric flow rate. Paano mo sa-solving calculations kung hindi mo naman alam yung flow? Of course, this has been discussed partly dun sa reports on sensors, but this time it focused on some calculations. So again, it's important that we are able to determine flow rate so that all other calculations regarding pump power requirements and the like could be made tangible. So, kailangan din syempre ng regular flow rate monitoring sa mga operations kasi doon nakabase yung inyong operations. Paano malalaman kung gaano nasa ice cream plant kami para malaman namin kung gaano katagal pa bago matapos yung production run, titignan namin ano ba yung flow rate ngayon. Tapos pag sinabing, sir, hindi kami makatakbo at 600 liters per hour kasi hindi maka-keep up yung cooling. I-reduce namin to 300 liters per hour, and then of course, you know, that would automatically double the amount of time needed to finish the run and therefore would affect stuff like yung scheduling nyo, yung manpower, how many tubs of ice cream you could produce, and kung madedelay ba yung takbo nyo na dapat tapos na bukas, mag-extend kayo ng kalahating araw. So mahalaga ang flow measurement among other things. And dyan din of course yung HACCP measurement of pasteurization. Halimbawa, pag continuous pasteurizers yung gamit nyo, mga ganong bagay. So this is the most common type of flow measurement device. It's called a U-tube manometer. Okay, it's a U-shaped tube. And then meron kang fluid na laman dyan, which is number one, it should be different and much denser than the fluid of interest. Okay, so typically mercury is used. So halimbawa, dito yung water yan, ito yung water mo, tapos nandito yung mercury. So we know that because mercury is very dense, it doesn't really mix with water, so hindi naman issue yung contamination in this regard. So it's important that we still cling on to the Bernoulli equation sa puntong ito. So kung makikita natin, meron tayong apat na points dito labeled conveniently 1, 2, 3, and 4. Okay? So using the Bernoulli equation, and then we assume, for example, na because the density of mercury is much greater than the density of water or other fluid, then nagiging negligible yung terms na may kinalaman sa fluid density, thus making our Bernoulli equation calculation easier. Okay, so collapsing this equation with this assumption, if you have a pressurized vessel here at point A, the pressure at A will then be equal to the density of mercury multiplied by your G, and then Zm, which is the difference in the height of the manometer fluid, plus the atmospheric pressure at point 4, which is open to the atmosphere. Okay, so ang nangyayari kasi dito, di ba, nag-i-increase yung pag nag-i-increase yung pressure mo dito, tinutulak niya yung manometer fluid along that common cross-section area. So kanina flat yung fluid mo. Tapos pag tinulak mo siya, then mag-form siya ng parang letter J. Mas mataas on one end than the other. But of course, we could assume that itong points 2 and 3 parang equal pressure yan. So therefore, yung pressure at this point is equal to the pressure contributed by this. And the pressure at this point is equal to yung pressure ng height ng column ng mercury and then the atmospheric pressure. Equal yun lahat sa pressure at A. Okay, so actually, even if you don't memorize these equations, you can see a diagram and you can calculate what needs to be calculated. No, binaseline mo lang to, no? Okay, so in this example, we now have two fluids which may have different densities. Let's call them A and B. They're both in enclosed vessels. Okay, so we cannot easily disregard yung density term ng both A and B. But again, we could set up the equation so we know that this is ito yung isang side ng equation, ito yung kabila. Kung gusto mo silang ilipat, din gawin mo lang minus sign yon. So pressure at A represents this one, PA. Then the rho GZ1 is this. Okay, kasi yung height ng column ng fluid A, may pressure din siya on top of the pressure of pressurized vessel A. And then you have the density of mercury multiplied by the height difference of this column from your baseline. So yun yung pressure na ina-exert niya. And then yung pressure na ina-exert ng fluid B Okay? So yung height ng column na yon multiplied by the density niya in Z. And then finally, the pressure at vessel B. Okay? So sinimplify na lang dito, naging minus sign na tong dalawa kasi nilipat na siya. And to get the difference in pressure between A and B, so you just move B, PA minus PB on one side, and then all the other terms sa kabila, which is basically G multiplied by the differences in density multiplied by height ng mga columns mo, plus your Z3. Actually, pwede mo ihalo to para isa na lang yung multiplier mo na Z, no? Anyway. So maybe right now you're wondering, Sir, bakit pressure yung sinusukat natin? Akala ko ba flow rate yung topic? Well, yun nga kasi to be able to measure flow rate, you have to measure the pressure difference, for example, on two sides. So later on, we'll see pag nag-connect-connect na lahat to. So there are different terms for the types of pressure. Static pressure is defined as a thermodynamic pressure of a moving fluid. Baka tanong nyo, bakit static gumagalaw nga siya? Isipin nyo na lang ganito, no? When you're in a moving vehicle that's under constant speed, hindi nyo nafe-feel, di ba? Parang smooth lang yung biyahe. Pero pag bigla kang promreno or pag naman sana bigla kayong mabangga somewhere, then dun nyo nafe-feel yung jolt. No? So, isipin nyo na lang ganun. Kaya sa static kasi kapag gumagalaw ka ng dire-diretso ay hindi mo mafe-feel yung jolt. Okay, sabihin na lang natin ganun. Alright? So anyway, static pressure in this case is measured by ganun pa rin, Bernoulli equation pa rin yung gamit natin. So we could see here, here's the static pressure niya. Parang ginawa mo lang, binutasan mo yung pipe tapos hinayaan mo mag-ano siya, umumbok siya. So yan yung pressure niya, yung upward na pag-umbok. Kasi kung walang pressure yan, hindi yan lalabas dyan, di ba? Kasi alam natin ang pressure ay tulakan ng mga puwersa. Okay? So if you take this one for example, static pressure, the pressure at point 1 is equal to the pressure at point 3, which is equal to the atmospheric pressure, plus the pressure at of the column of fluid above it, so yung Z1 plus Z2. Okay? So yan yung nakapatong sa point 1 na yun, yun yung nakapatong sa kanya ng mga bagay. Yung atmosphere and yung dalawang column ng fluid. Which you could simplify this. Remember we mentioned that gauge pressure is based on how high it is above the atmospheric pressure. So therefore, ang PATM mo, ang reading yan sa gauge ay 0. Kasi pag atmospheric pressure, nasa 0 yung needle mo. Therefore, if you're gonna look at the gauge pressure, it would simply display the product of the density, the acceleration due to gravity, and the height of the column with respect to your reference point, which is in this case 1, so yung Z3. So by the way, kung napansin nyo, parang higanting YouTube manometer pala tong area na to, no? In this case, for example, if yung point 1 nag-move siya sa point 4, if it hits a snag and its velocity becomes 0, law of conservation of energy dictates that that energy has to go somewhere. Of course, in Bernoulli equation, ganun din naman, di ba? You have a pressure term, a velocity term, and a height term. So, if we're gonna look at those terms, okay, so you have the pressure term and velocity terms here equated at point 1 and point 4. At point 4, yung velocity niya ay nagiging 0 nga. Okay? Kasi 0 yung velocity. Therefore, itong 3 terms na lang yung i-consider mo. Then if we isolate the pressure at point 4, then it would be equal to the pressure at point 1 plus a function of its the velocity at point 1 multiplied by the density over twice the gravitational constant. So, yung stagnation pressure, which is defined as pressure at zero fluid velocity, will be equal to the static pressure plus the dynamic pressure. So, yung kabuuan yan. So, with that being said, the dynamic pressure then is the difference in pressure from the your static and stagnation pressure, and is directly proportional to the difference in height between these 2 points. And it's simply the pressure of the fluid due to its kinetic energy. Okay? So yung term kanina na inad mo from P1 to get P4, that itself is equal to the dynamic pressure. So the pitot tube is a contraption invented in the 1700s by a man with the same surname, and it's used for measuring fluid velocity through similar means as the U-tube manometer. Typically, ginagamit siya sa mga aircraft. So you might see this in some aircrafts. May L-shaped protrusion parallel dun sa direction ng travel. So the principles are similar. They measure total pressure and static pressure, and you can use that to calculate the velocity. And although you do use a tube coefficient, which is a function of the pitot tube itself. Okay. So, yun din siya para mo lang kinabit sa isang U-tube manometer, yung device mo, where air comes in through this direction. So we could try doing the sample problem in the previous slide. Another type of measuring device is the orifice meter, which introduces a ring which constricts the diameter of the pipe by a certain amount. And of course, how it works is still, you measure the pressure at points A and B and correlate that to the velocity at points A and B. Okay, this is still based on the equations as the Bernoulli equation, no, in a way. So, kung kinabit mo yan sa isang pipe, you would just have a manometer reading. And if you calibrate the fluid is the same, no? Same fluid yung nandyan sa part A at sa part B. So, you can actually calibrate the height readings to become pressure readings instead. No? Mamarkahan mo na lang yan. Okay. So again, this one relates the velocity to the constriction of the cross-sectional area. Right? Because as we know, when you constrict this, yung continuity natin, bibilis yung para unimpeded yung flow niya, ay bibilis yung daloy dun sa constricted area. Okay? And that has a corresponding pressure drop. So you can use this to correlate the velocity of the flowing fluid. So this is the working equation for measuring flow using the orifice meter. So the velocity then could be determined using the difference in pressures at points A and B, as well as the known diameters, known density of the fluid, and C, which is a orifice coefficient, which is a function of the location of the pressure taps and Reynolds number and pipe diameter ratios. So ganito lang po yung itsura ng mga orifice flow meters, no? Of course, they're obtrusive and obviously they have frictional losses because they suddenly constrict your fluid, and therefore they are not always the best option unless talagang wala kang space. So one very good advantage is they're very compact, as you can see. So to counteract the disadvantage of friction losses from orifice meters, you could use a Venturi tube na dahil mas gentle yung kanyang constriction and expansion ay less yung frictional losses. However, the disadvantage would be is that kung yung orifice meter, ito lang yung size, yung Venturi tube, mas mahaba siya ng di hamak. So you need to consider that in your, let's say, plant installation na maglalagay ka niyan saan and enough ba yung space mo. Definitely, the larger the diameter of the pipe, the longer the tube will be. Okay? However, it operates on a similar principle and therefore has not exactly the same but somewhat similar equations. So we will not go at understanding the derivations for this, but at least we know that, okay, ganun pala gamitin yun. So other passive meters include the variable area meters. So ayan, meron siyang parang float, and kapag mas mabilis yung daloy, mas mataas yung posisyon niya doon sa tube, and then may gradations yan that correspond to the velocity of the fluid. Of course, needless to say, this needs to be calibrated to the fluid's density. So it's not something that would work the same way kapag magkakaiba yung fluid na gamit mo. You could do, however, use a conversion factor na lang siguro kung may gradations dyan and you multiply it by something. Other flow methods are turbines. Of course, yung mga, ito siguro yung napapansin ninyo sa metro ng tubig natin sa mga bahay, no? So, mechanical, may moving parts which could break or at least nakaharang sila dun sa one side to the other, okay? But it's pretty commonplace, simple technology siya. This is the same tech as in yung mga, pati yung sa mga speedometer ng kotse, no? Using turbines, gears, magnets, and the like to multiply the number of rotations with the expected fluid flow per rotation. And we've also discussed this in the sensors part, pero yun, ginagamit din ito. This particular one, I think, ay ginagamit sa petroleum, no, yung ultrasonic flow. So of course, you've seen the other types of flow meters under sensors. So if you want, you could check back on that segment para ma-refresh kayo dun sa may mga kinalaman sa fluid flow.